Hello, everybody. Trying to get you your money's worth. So we are going to take a few steps into the material, although it's the first day of school. So with that, we just finished going over the syllabus. And you should know already that how to access our course webpage. This is just a link to WILE courses. Our book. This is our book, The Statistical Rethinking, the second edition. And if you're curious at all, Richard McElreath also is pretty active on Twitter. It's great supplementary reading. Of course, it's not required. I think there are some helpful links to purchase the book. You can take a look at the first 2 chapters for free, and a ton more things. So here is our book. I mentioned I'm a big fan of this book. So what I'm calling the immediate software for this course, R and RStudio, you need to install them together in order to follow along. R has recently put out its 4.0, and probably already something else. It's probably 4.0.1 or 4.0.4 already. My recommendation is that you go ahead and update your R as far as possible so that we don't have weird mismatches in code. They actually made a few structural changes in 4.0 that I forget off the top of my head. They don't have anything to do with statistics. They're more with how I think text variables come into R. So go ahead and update your R while you're at it. That can sometimes take far longer than I know we all would like. That's just a recommendation. Later on, as we progress, I would like to introduce you to useful software that you can use, hopefully, when you leave this course for your research. And so, eventually, we will start to use the BRMS package, which I think is absolutely a phenomenal package. I've used it a bunch. It's very, very flexible, very easy to use, Bayesian package, of course. And it depends on our stand package, and it depends on our tools. Our tools, I'll just point out right now, are a pain in the behind to install. Just go ahead and get that out there. When it's time, I will uninstall it on my computer and reinstall it just to show everyone how it is done. Hopefully the R tools for the latest version of R, they made it as easy as possible to install, but it has been a pain. Just pointing it out there. Don't worry about the stuff that is happening later on. For now, when you get a chance, install R and RStudio. And then we'll deal with our tools, our stand and BRMS later. Okay. Now we got all that boring stuff out of the way. I never know how many statistics courses people have before they come to this one. So when you're teaching Introduction to Bayesian, I like to start from the beginning. So what is statistics? Well, statistics is the art and science of extracting meaning out of data. And specifically art and science, especially when we start talking about Bayesian analyses and we start talking about the concept of prior distributions, which literally quantify your prior beliefs, we start to really think about this art component a lot more. Science, well, of course there's a science to it. Something like p-values, which you learn pretty early on, I like to talk about as an accumulation of evidence against the null hypothesis. So there is a lot of both art and science in extracting meaning out of data. Not to mention that we need to have subject matter expertise. When I talk about model building, I definitely want to be driven primarily by science. I like to be driven primarily by science before I start to deal with distributions, interactions, information criteria, all the buzzwords that we'll talk about a lot more in the future. I thought I would include a few of my favorite definitions of what statistics is. One guy, I don't know how much of you guys have heard of him, is Hadley Wickham. He is the creator of ggplot2, probably a major contributor to Tidyverse, and is also involved pretty heavily with RStudio. He says statistics is an important tool in the data science toolbox, provides a coherent framework to think about random variation and tools to partition signal and noise. I like that. I like the idea that even the best statistical model will leave something random. The best statistical model will extract all the signal from the data, all the systematic variation, and leave only residual noise. In fact, if you're taking a time series class, sometimes you will call it white noise. When I took a time series class, that is how my professor presented it. So when we are building statistical models, we don't try to model the noise, right? We leave it alone. We try to extract the systematic variability, leave the random variation, the noise alone. I always also liked the definition by Joe Harden from Pomona College, great liberal arts college. Statistics is using data and knowledge about randomness to condense, communicate, and contextualize information and provide insight into the setting from which data came from. And I think that Dr. Harden here is talking about the fact that to really interpret statistical models, we have to know where they came from. We have to know about the data generating process. The more subject matter expertise we have, the better we're able to contextualize our findings. I was classically trained as a statistician, so I always imagine working with somebody from agriculture, somebody from the hard sciences, somebody from social sciences, somebody from business, and it's a true collaboration where the subject matter expert helps me better interpret my fancy statistical models. Just some thoughts about statistics. Statistics is an art and a science, but boy, are we a young science. Math is what, like 500 years old? The mathematicians can correct me. That could be your participation for the week, is correct me on how old mathematics is. Statistics is very, very young. The American Statistical Association, as far as I know, is the second oldest academic association in the United States. The only one older is the American Philosophical Association, and you cannot, apply, or you cannot just pay money and be a part of the American Philosophical Association. Too many people want to be philosophers. American Statistical Association definitely still exists. I'm a member. It puts on, in regular years, it puts on the joint statistical meetings, which are a great deal of fun. Something like 15,000 statisticians from all over the world. One of the biggest job fairs. If you are somebody who is into statistics, or you are a frequent applier of statistics, I would strongly recommend that you check out the joint statistical meetings, especially if they're in a fun city like San Diego or Austin or Portland, Seattle, etc. Okay, so I think it's great fun that these folks were actually some of the founding members of the American Statistical Association. Brownie points, Alexander Graham Bell and Andrew Carnegie hardly need introduction. Martin Van Buren was, I believe, the 8th president in the United States, was a statistician. 1894, Carl Pearson introduces the standard deviation. We use it as if it's second nature. Maybe nerds like me do, but in 1894, this was breaking news, the standard deviation. William Seeley Gossett, the chemist from Guinness, introduces the t-test 1908. If you're interested, you can still read the original biometric cut paper on Wikipedia. Don't. It is written in a rough English language. It's a tough read. I tried. Sir R.A. Fisher, somebody I say is considered the father of statistics, but is definitely not a nice person. Many reasons that I don't want to get into right now. definitely somebody who I appreciate the contributions from statistically, but not so much in other areas of life and science. Sir R.A. Fisher introduces the null hypothesis testing in 1935. He was a geneticist, and so he invented statistics as a way to do his science. It's kind of interesting to think that almost accidentally invented statistics. John Tukey introduces the box plot. You know, I think Tukey got a Medal of Science fairly recently in the 2000s. And the box plot is one of my favorite graphics. I think it's very, very informative. That's a misspelling, and I misspelled a key word there, guys. If this was an in-person teaching, then I would definitely expect people to be yelling at me for that. So that is not how you spell Bayesian. However, when I was going through this, in 1989, the Bayesian WinBugs project begins at Cambridge. WinBugs is probably the most popular Bayesian analysis software out there. It's possible that JAGS is now catching up in popularity, but WinBugs was the tool to do Bayesian analysis for a very long time. You used to download a standalone software package that was buggy, to say the least. Cambridge. 1993 was the initial release of R, the program we all know and love. And then I said, you know, for a while, that was the last point I had in this slide. And I said, man, we've had a lot of things happen since 1993. So I thought it would include Julia in there. Now, I know Python users are going to tear me apart. Python was introduced around the same time as R. But from everything I read, and hey, again, that could be your guys' participation, okay? From everything I read, Julia is supposed to be the next big thing. Now, I used Julia maybe 5 years ago as a part of a class to kind of get out there and try some things. And I was unimpressed, but I know that a lot of things happen in 5 years, especially when we deal with computer science and programming languages. And if there was something besides R and Python that I was going to give a shot, I'd probably give Julia a look. It's supposed to be faster, I don't know, something like 30 times faster than R. Again, participation, correct me on it. Get the conversation going. Okay, preamble. So our author has a fascinating figure on page 2 of the book that I didn't bother reproducing because it is meant to be confusing. I didn't want to have a deliberately confusing figure in my slides. But the idea is the figure would be like a flow diagram, a decision diagram for which statistical tests to use in what situation. And we've all seen that in intro to stats kind of courses, intro to stats coursework, if you have categorical data, or if you have normal, quantitative data, your sample size is under 30, use that. If your sample size is over 30, use that. If your standard deviations are equal, use this. Why would you ever assume that to be the case, right? So I strongly endorse Dr. McElreath's recommendation to focus on building models for the data generating process. So we'll be asking ourselves questions. How did our exact sample come to be? What machinery, conceptually speaking, what machinery has produced our data? Where in that machinery is our systematic variation, the signal, and what is just random noise? So by focusing on modeling, model building, and the data generating process, we'll actually be able to rank models for the same data set, that's key, the same data set, according to their predictive ability, according to their information criteria. Some of you may have heard of the AIC. Some of you may have heard of the BIC. Some of you may have heard of the QAIC. In truth, there's probably like 50 information criteria out there. They are frequently used. They're frequently misused. We have a whole unit on that. Point is, when you're building models for a given data set, you can test hypotheses by comparing different models. In fact, every model represents a set of hypotheses. For example, if you include a covariate into a model, you're saying, hey, this covariate matters. If you have a model that doesn't have that covariate, you're saying that that covariate doesn't matter. I'm going to include it as a part of my random noise. Remember that quote by Joe Harden? We can see if the relationship between a quantitative covariate and the outcome is linear, quadratic. We can see if there are various interactions. We can do all kinds of things, and I will be harping on, is there an important feature of the data generating process that our new models try to parse out? So that again just follows what Dr. McElvey includes in the beginning stages of the book. So our author also gets into overfitting pretty early, which I think is great. Information criteria are a complicated topic, but I think overfitting, I hope, is relatively easy to wrap our minds around. So I thought of a heuristic, little heuristic tool. So suppose our job is to pack gingerbread people, we don't know if they're men or women, they're gingerbread people into boxes. So this is our data right here, guys. Here's our data. All right, we have a nice little sample size of 3. Here are nice gingerbread people. So suppose that model A fits our observed set of ginger people best. So how would I find a box, think of it as a box like a model, find a box that fits my data the best? Well, I probably, pick up the features. So, get nice, arms, and, here's the legs. Here's the legs. Oh, there's another arm. Okay. I'm not a very good artist, especially with the stylus, but this is my model A, right? It fits my observed. Pretend I can do that. All right, give me a chance, guys. There we are. There we are. That's a great fitting model. That's well fitting. Yeah, that model right there, that fits the data really well. Okay. Well, suppose we came up with another model, model C. A model that doesn't fit our observed data very well. Well, what I could do is, just kind of almost blur my eyes a little bit. Oh, I don't know, if I blur my eyes enough, the gingerbread people look a little bit like an oval. So maybe like an oval like this. So an oval like this, I could put the gingerbread person into that oval. It's poor fitting. Ooh, my handwriting is really deteriorating. I apologize. I'll get better with the stylus. Give me a chance, guys. Poor fitting. It gets the job done. It picks out the broad features of roughly elliptical cookie, but boy, it fits a lot worse than A. So something in between is clearly best. And I need to erase these. We need something that fits better than model C, but not so well as to just pick out our exactly observed data set. So model B, I don't know, it might look something like a little bit more angular maybe. Something like that. So we're talking about making a model flexible enough to accommodate, that's a tough word with a stylus, unobserved data. Unobserved ginger people, like these two. Model A wouldn't, these would break if we put them into model A, although model A was best fitting. Model C, we can put anything in there, but we can do better than Model C. So what's the takeaway? Model A overfits. Model C underfits. Model B is just right. And I know I'm doing a lot of arm waving right now. We will eventually get to information criteria, frequentist and Bayesian. But since our author felt that it's important to kind of introduce overfitting as a danger now, I feel I wanted to get this curious little heuristic in front of you early on as well. I'll get off my soapbox now. So the other thing I wanted to do towards the end of today's video is to begin to connect frequentist and Bayesian statistics. These are, in fact, the two big camps in statistical analysis. They're not, depending on who you talk to, people sometimes feel very strongly about one or the other. And I mentioned in my first video, I'm not here to convert anybody. I never had a Bayesian class until I saw for myself that the analyses worked better in a Bayesian world. I still use frequentist analysis. In fact, most often I don't trust the Bayesian analysis, so I begin with a frequentist analysis, and then it's usually not complex enough or not flexible enough, but then I start to iterate with the Bayesian analyses, slowly building up until it's more and more complicated. So the next bit of slides, starting from here and really through pretty much the end of this set of slides, I'll be trying to connect frequentist and Bayesian statistics. So this is just the beginning of that. So the first formal distinction in the frequentist world, and that is probably how most of you learned your introduction to statistics class. In the frequentist world, we think of parameters being things like mu, beta, sigma, rho, not their sample counterparts, right? Not x bar, not beta hat, not s, not rho hat. Parameters, population parameters, are unknown fixed constants. In the Bayesian world, parameters have distributions called priors. That's not the only name for a distribution of a parameter, but this is the name for the distribution of the parameter before any data is collected. Handwriting. We don't have to collect data. In a Bayesian world, we actually don't formally need data at all. I can run a full Bayesian analysis with no data at all. In fact, I can make a prediction about 2020 election here on the spot, and I don't need to see a single data point to make what I believe is a 99.99% accurate call for how Wyoming and Hawaii are going to vote. Don't need any data. I am not aware of a single poll. I haven't seen a single poll for either Wyoming or Hawaii, but I'm pretty comfortable calling those two states. So you can probably intuit why that's the case. What I'm thinking is, as a parameter, is proportion voting for a given party, Republican or Democrat. And in my mind, these parameters have priors. These priors are distributions that define my understanding of the world before any data is observed. In a frequentist world, I would assume that these parameters are unknown fixed constants, and I use data to find their estimate. So, speaking of estimation, estimation in a frequentist world is an exercise in maximization. Estimation is an exercise in maximization. We will make the likelihood function, I'll define likelihood probably next time, but if you're doing traditional frequentist statistics, you compute the likelihood function and then you pick the value of our parameters such that the likelihood, or the log, the natural log of the likelihood, is as large as possible. Let me repeat that. You pick the value of the parameter such that the value of the likelihood, or the log likelihood, is as large as possible. So actually, let me draw. Log likelihood. Just hang on till next time about the definition of what that is. Most often it's a shape like this. So if I was going to maximize this function, this curve, well, the maximum occurs right there, and the fixed value of the parameter where the maximum occurs is right there. So in a frequentist analysis, there is just one estimate. It is the estimate that maximizes the log likelihood. Right? Estimation is an exercise in maximization. By the way, R will do this iteratively, right? A lot of maximization can be done using pencil and paper. If you're taking a math stat class, you would do this using pencil and paper. But if you're running an R model, it does so iteratively. It finds, builds this likelihood surface and then finds the maximum, and not computationally, iteratively, not analytically. Okay, what about Bayesian? Estimation is an exercise in random number generation. It's not, and I'll put random with a star. It's not really random, or it's not truly random. It's not just any old number, but it's number generation. Random number generation. You are generating values of your parameter from what you hope to be a target function. And I'll define much more of that later. But your estimates in a Bayesian world are not just a single value. Because you produce lots of parameter values, what you actually get is a distribution. So estimation produces what is called a posterior distribution. Which is the distribution of your parameter after data has been observed. And that looks like, by the way, theta is just any old parameter. Theta is just a generic parameter in statistics. I know I don't have it up there, but theta is often used to denote any old parameter. So, you have a distribution. Based on the numbers that you generate, here is the distribution. You don't have just a single value. Here is the posterior distribution. Now, it's up to you how you want to summarize this distribution. You can take a mean. Mean of what? The data? No, not the mean of the data. The mean of the values of the parameter that you have generated. You can take a median of what? The data? No. The median of the parameters that you generated. You can take a mode. And you can see if you take a mode, that produces something similar to what you see on the left-hand side of the screen with frequentist estimation. So I'm afraid that in this arm wavy portion of the course, I'm getting a little too arm wavy. So I'm actually gonna go ahead and shut it down for today. I wanted to just get us thinking a little bit about frequentist and Bayesian statistics and overfitting. We will put a lot more math. There's some math coming up. There is some mathematical notation. So we will get more concrete. I'm stopping here because I don't want to overload us in the first day of school, but we will get a lot more concrete, just introducing stuff in this first slide. Thank you all very much for your attention. Hope everyone's safe. See you guys next time.